Simplifying radicals. The key thing is you can't have radicals in your denominator. The other key thing is to get rid of them when you have binomials. So binomials are like I've got a regular number, like 1, 2, 3, half, -4/3, anything that's rational, which means you can write it as a fraction, plus or minus, then you have some radical, like a √2. Or maybe you have like a -√3, or maybe a plus a 4 √2, or minus a 5 √7. Just anything that has a radical to it. Plus 100 root, I don't know, 5 maybe. All of these are binomial radicals, meaning they've got two terms in them. One of them's rational, just a nice pretty number. The other one is a square root of something or a product of a square root of something in a number. These are all binomials, and all of these binomial radicals have conjugates. Okay. The conjugate for this one would be 1 minus the √2. See, I just have to change the sign in front of the radical. The conjugate for this would be 2 plus √3. The conjugate would be 3 minus 4 √2. Conjugate would be 1/2 plus 5 √7. The conjugate would be -4/3. And I change the sign in front of the radical section, minus √5. Okay, those are all the conjugates, and actually each one's conjugates of each other. So these two, I can say this is this red one's the conjugate of the blue, or the blue's the conjugate of the red. They are conjugates of each other, and conjugates have this miracle thing happen when you multiply them. So in your case for your problem, here's your expression. It's binomial, a radical part and a integer part. The conjugate is change the sign in front of the radical. So it's not about where it's located, it's that it is a radical. And so instead of a plus √2, I use a minus √2. But I keep the sign on the one there, on the rational part of it. And then I have to do the same thing to the top. So I decide my denominator, what I'm multiplying by, and then copy that to the top. And then the rest of it is just, I'm going to erase my conjugate lists there, my examples. Oops, I did not want to copy that. I want to cut it. There we go. And so now we just multiply these two. All we had to do is know what the conjugate was and then multiply them together. So on top, let's do this math first. So when you multiply here, you're taking the outside 1 times this outside -1, which is -1. And then you're taking this inside √2 times this inside √2, and that gives you an inside √4 like that. And then I have to take this 1 √2 times this -1. So I'm really multiplying the -1 times the 1 and times the √2, and it looks like -1 √2. 1 times -1 times the √2, and I go 1 times -1 √2, I go 1 times -1. So there's my numerator right now. Now there's some cleanup we can do in here, and we'll do that in our next step. But right now, realize that like this -1 √2 and this -1 √2, those can be added to give you -2 √2s. And we can square root the 4, 'cause square root of 4 is just 2. So we can clean up some of this stuff. Now let's do the denominator, because the denominator is really the problem here. We can't have any radicals in the denominator, so this is what we do to get rid of it. We just multiply it by the conjugate here, and let's see what the results are. So I go 1 times -1 is -1. And then I go √2 times √2 is √4. So there's my first multiplication, and maybe I should do that in dark blue to map the arrow I drew there. And then I'll do a red one here. So we go now √2 times -1. So I'm doing the 1 on the outside times the -1, which is -1. What color am I? Red. And then times a √2. Then I have to take the -1 times the -1 √2, which gives me a +1 √2. And lastly, I have to do a -1 times -1, just +1. Now I'm going to clean this up a little bit, and I'm going to start with my numerator. For the first one, -1, and the square root of 4 is a 2, so now it's -1 times 2. These two are like radicals, so I just put them together. -1 minus 1 is -2, counting the number of √2s I have, and then I've got that -1. And then on the denominator, I've got a negative 1 times the square root of 4, but the square root of 4 is just 2. So it's negative 1 times 2, which is negative 2. This one and this one are the same root 2's, but one's minus, one's positive, so they add up to a 0 root 2's. And then finally we got plus 1. And now I'm ready for almost my last step. That's negative 2 minus 2 root 2 minus 1. We're going to combine those two in just a second. And here I got negative 1, so I get negative 2, oops, sorry, negative 3 minus 2 root 2's. So I've put those together all over negative 1. And you might very well stop right there. Generally, though, in negative 1, we don't leave on the bottom because everybody's divisible by 1. And so why leave a denominator if you don't have to? Now, I am going to get rid of that negative 1 by dividing everybody by negative 1 up here. Or you could think of it this way, and this is the formal way. You say, well, I can factor a negative 1 out of the top, and it makes some positive 3 plus 2 root 2. And it's all over this negative 1, and so those cancel. And there's your final answer. But you can see the end result here is just taking this negative 1, dividing them both by that negative 1, you get 3 plus 2 root 2 right there. And that is your answer. If you ever wanted to check an answer to see if you were correct or incorrect, um, you could throw like the original problem into a calculator. It looked like this. You'd have to use parentheses, and you could go second square root of 2 plus 1. So there's my numerator divided by parentheses, the square root of 2 minus 1. And you'll see what decimal value, oops, gotta be a little bit careful here. I gotta make sure that minus 1 is outside of the radical. So I have to arrow to the right there, and then go minus 1 in parentheses. And so there's the original problem, and there's the decimal value. Then here's my answer, if I can slide that over, the 3 plus 2 root 2, and it should yield the exact same decimal, right? Because they're equivalent forms of each other. Just one doesn't have the radical at the bottom, and that's how we like it in math. All righty? So that's kind of the gist of it. So if you ever see a radical in the bottom, you'll see me do some step to get rid of it. Let's look at this one now. We're just applying some of this stuff. Find the length of the diagonal of the rectangle. So rectangle tells us these are right angles. They've even drawn them in there for you. Trying to find this. So this is a right triangle. I just focus on that. And right triangles have a squared plus b squared equals c squared. So I'm going to label my sides a, b, and c. And then the Pythagorean theorem, a squared plus b squared, leg squared plus leg squared equals hypotenuse squared, right? The hypotenuse always across from the right angle. So now I plug in my numbers. Root 48 squared plus the other leg, leg b there. Root 192 squared equals c squared, which I'm trying to figure out. Well, when I square root, it just undoes it. Yep, it's there again. And so c squared is equal to whatever 48 plus 192 is. So 48 plus 192, 240. So c squared equals 240, and so c equals the square root of 240, right? We're square rooting this side to give us c. We square root this side, and we've got this square root of 248. Now that's a number, right? The second square root of 248, or 240 rather, is 15.49. So C here is about 15.5 inches, centimeters. They don't tell us units. Your teacher does not want that number. Okay, they want this number, but they want it simplified. So I've got to figure out how 240 breaks down. So when I'm simplifying radicals, I start with whatever they give me, whatever's under the radical, called the radicand. I just take the radicand and I start to factor him. Now, ideally, when you factor him, you try to factor him into as big a chunks as you can because it helps you speed up the process. So I did 24 and 10, kind of an obvious one, but I can't square root it 24 and I can't square root 10. So I just keep factoring this thing. I wish I'd left myself a little workspace because it looks like I'm going to run out of room. Because right now I realize, hey, I'm going to have to do quite a bit of factoring because I don't know how 240 really breaks down. All right. So if it's a big number like 240, you generally attack it this way. I'm going to try and find a space here to work. I'll just do it down here. Take your 240. Remember, it's underneath this radical. Just start factoring it. Make a nice big factor tree. Always bring your branches all the way down. Anytime you factor something, these are all multiplying here. And you can factor in big chunks, however you can get it. So anyway, there's the complete factorization for the number 240. And so if it's a square root, what I'm looking for is two of a kind, because when you have two of a kind, they're a perfect square. So let me show you what I mean by that. Like when I see a pair of twos, I can think of that as, oh, that's just the square root of 4. Here's another pair of twos. I could put those together. That's another 4. And then the 3 times 5 are still there. And the reason I want to see these because I can take the square roots of those. So I can square root that 4, which is 2. I can square root this 4, which is 2. And I'm left with 3 times 5 in there, or we write 4 root 15. And that's your simplest answer for part A up there. Um, Now, probably not the quickest way to do it. Now that I know what the answer is, the best way to factor 240, it looks like, would have been to go, oh, that's just 16 times 15. And it is. And then I could square root the 16 and the 15, but the 16 only gets square rooted, but the 15 cannot be. So I get to the same answer if I could see that factorization quickly. All right, so that's how we simplify 'em. I imagine we'll have to do more of those as I go through here, so don't stress about it yet. There's your final answer, by the way, the 4 root 15. So let's get rid of all that. All right, now it says find the perimeter of this thing. Oops, let me write that answer here. C equals 4 root 15. And again, another check you could do is I could now take the 4 second square root 15. It better be equivalent to root 240, and it is, so I know they're the same thing, and I've got the right answer. All right, let's find our perimeter now, this rectangle. So we just got to add up all the sides. Thank goodness it's a rectangle because I also know these opposite sides over on each one. So I go root 48 is one side plus a root 90, 192 plus another root 48 plus another root 192. Add up all the sides. That's your perimeter. But let's go ahead and put those two together. That's 2 root 48s plus 2 root 192s. We just got to simplify these guys. All right, let's see if I can go big this time. 80 or 48 is 16 times 3, so I can square root the 16. I already got a 2 out here, so it goes 2 times square root of 16 is 4. 3 stays in, so that is 8 root 3. 192, let's see here. Wonder if 16 goes into that. 16 does. 16 times 12. So I can take the square root of 16. I've already got a 2 outside. And so I can get it to 8 root 12 pretty quick. And most students might stop there, but you can't really. And the reason you can't is because you got to check out that 12. And that 12 that's still under the radical is a 4 times 3, and I could square root 4. So I bring out that 2, the square root of 4 is 2, and it gets multiplied by the 8 that's already out there. There we go. And that is your perimeter. Okay. And again, if you ever want to check these things, I'm going to just add up all 4 sides. I'm going to go root. Actually, I'll do it like this. I'll go here. I'll go 2 of these root 48s. So I'm using this form of it right here. Plus 2 of these root 192s. That's the perimeter of it. But now I'll type in the answer I got as my perimeter. And it better be the same thing. There's the 8 root 3 plus a 16 root 3. I don't know why I've left them separate because those two add up to 24 root 3s. I didn't recognize they both had root 3s. So I'm just going to type in 24 root 3. And you can see it's the same number. So 24 root 3 is equivalent to our perimeter, and that's the simplest form of it. So that's what we give for an answer, 24 root 3. Right? These are both root 3 expressions, so we can just add their coefficients. Quadratic equation, let's solve it. So um, I'm going to first see if it factors, right? So I would use my A times C. It's called the Australian method. I just learned that the other day, and that's 6. And so when you use the Australian method, you go 3x and 3x, and then you got to put a 3 down under because you're going to cancel that 3 out in a little bit. Two numbers that multiply to 6, but they have to add up to the middle term, which is a b, or the b term, which is a 5. Let's see here. So like 1 times 6 multiplies to 6. And if the 6 was positive and the 1 was negative, they'd add up to a 5. But if one's negative and one's positive, they don't multiply to a 6. So I can't use that pair. I'm going to try 2 times 3. That multiplies to 6, and 2 plus 3, it adds to 5. So I'm going to put a 2 in one of these spots and a 3 in the other one. So I should have called that S. And they both have to be positives. And now I have to figure out how to cancel out this 3 down here. And to cancel them out, I can see that a 3 comes out of these two. And so I'm just showing you all the steps here. I would take this 3 out, giving me x plus 1. And then these 3's cancel. So there's the factorization. If you ever have doubts about that, you just check it real quick. You re-multiply it, and you make sure that it does give you the original problem. And it does. You can see it's 3x squared plus 5x plus 2. So I know that's the correct factorization. As long as you follow the steps for that down under method, it'll always work. Solve it though. So now remember it equals 0. And so now we say, hey, if two things multiplied, it's called the zero product property. This is like A, this is like times B equals 0. And if two things are multiplied and give you a 0, one of them, either the A, which is 3x plus 2, equals a 0, or the B, an x plus 1 must equal a 0. We just solve those, subtract the 2, divide by 3. There's one of your answers. This one's easier. Subtract 1, and there's one of your other answers. Solving by factoring. All right, that's page 1. Let's go to 13. So they said express your answer in simplest radical form. That tells me that this one doesn't factor. It's going to have square roots in it. Okay, I could try to factor it, and if you aren't told like a little clue, like this stuff is a little clue to us, you would just try to factor it, and I'd go, oh, this is -10 when I take A times C, and I'd go 2x and 2x, and I'd put a 2 down under to cancel that out. Numbers that multiply to 10. And as soon as I start to list them, it's 1 and 10 and 2 and 5. None of those can add up to a 2 in the middle. And that means it is not factorable. And I just stop trying to factor it and I go to plan B. And plan B for quadratics is generally the same thing for everybody. Usually we just use the quadratic formula. If you use the quadratic formula, it'll solve every single quadratic you ever get. So there's my A, there's my B, and there's my C. And I just substitute in. So negative of b, which is a -2. Then I have to take the -2 and square it, wrap it in parentheses whenever you substitute in to help you always get the right answer. Over 2a, not just 2, 2a. There we go. Now we just start cleaning up. So -2 is a +2. We just put 2. Square root of, I square the -2, but negative times negative is +4. And then I multiply these three numbers. Now, when I multiply those, the way I do it is this. I go, okay, I've got a negative times a positive. Oops. I've got a -4 times a +2 times the -5. So I've got two negatives that are getting multiplied together, and that's going to create a plus sign right here. And then I just figure out what 4 times 2 times 5 is, because I don't have to worry about the sign. I already know it's a plus. So that's 8 times 5, so that's 40. And I just keep working underneath that radical on that radicand, which we call the discriminant when we're using the quadratic formula. And I'm pretty much done, except for I have to see if I can simplify the radical. Okay. So in the flow of things, I generally tell students go like this. See here, that's 4 times 11. I can square root the 4, which is 2, so it's 2 roots 11. And then everybody's divisible by 2. I'm going to factor that 2 out so you can see it happen. Unmultiplied the 2, that 2 then will cancel half of the 4. So final answer, I'm going to write it up here as 1 plus or minus a root 11 over 2. Sometimes your teacher will break this up and write it this way. It's the same solution. 14. What are the values of x that satisfy the given equation? Value 1 is 1, value 2 is 9. What are all the values that satisfy it? Well, let's just solve it. So this is a radical equation. How do I know? It's got an x and it's under a radical. And that makes it a radical equation. And we have pretty easy steps for this one. Make sure the radical is lone. Isolate radical. And so uh, if I think about left side, right side of this equation, on the left side, oops, it's all a radical. There's no number out front, there's no number inside there or underneath, and there's no like 3 plus this. This radical is by itself. And when the radical is by itself, already isolated, then all you have to do is square both sides. And it is important to do sides, not individual terms. So I have to go, ooh, I'll square that side, and I'll square this side like that. On the left side, what naturally happens, happens. You just unsquare rooted it. The right side, it's not so natural. You have to distribute or do double distribution here because you got to use the formal definition of squaring. Take whatever is squared times itself. I'll run through this math here quick. X squared minus 3x minus 3x. Negative 3 times negative 3 is positive 9. I'll collect a few like terms. And now I notice it's quadratic, so I'll get it equal to a 0 by subtracting the 4x, it up under its like term, and I end up with this new equation, x squared minus 10x plus 9. And on the left side is where it equals 0, but I can make it on the right side equal 0. Either way, it equals 0. And then I try to factor it, especially since it's told me the answers are either 1 or 9, and I see that 9 there. 1 times 9 is 9, and if they're both negative, they add up to negative 10. And so x is a 1 or x is a 9. However, this was a radical equation. And radical equations, when you square both sides, can introduce an extra answer. So we got to check both these in the original problem and make sure they both make it true. Okay, so I'll check that up here. I'm going to check the 1 first. In fact, now that I think about this, we could have probably just checked it and solved the problem that way. So I put a 1 in, and the question is that, does that equal the same thing if I put a 1 in on the right? The answer is no, because this gives me the square root of 4, which is 2, but this side, 1 minus 3 is negative 2. So this 1 did not work. Now I'm going to try the 9 in there. So if I put a 9 in, it'd be 4 times 9, square root of 36. I get a 6 on the left. If I put a 9 in over here, 9 minus 3 is 6. It checks. And so value 1 only, value 2 only works. Only the 9. Only value 1 and value 2, neither value 1. Yeah, that's the only answer that makes sense. All right, I haven't read this problem yet, but notice right away, at least I notice, we've already done a Pythagorean theorem problem. And I see another right triangle right there and one right here. So maybe we're doing Pythagorean theorem again. We'll find out. Doesn't look like it. What is the length of AD? right here. Hmm. I don't think you guys have done trig yet. So let's just piece this thing together. This is 60 degrees, which makes this 60 degrees. And well, just because this one's 60 doesn't make them all 60. But if this is 60, and if I look up here, and this is 30, and this is perpendicular to this side, and it's hitting the vertex, this is going to bisect that angle. Trying to think if I can prove that. That's 30. This is 90. Yeah, I can prove it. So if this is 30 degrees right here, this would also have to be 90. 90 and 30 is 120. 120 plus 60 is 180. So I know this is 60. I know this is 60. Therefore, this has to be 60 to give me, again, a sum of 180 in my triangle. And that helps me a ton because, yeah, I can do the Pythagorean theorem, but I'll do it on this right triangle. And because it is a 30, 60, 90 triangle, this is going to be a perpendicular bisector. So it's going to cut this side into two equal pieces. And therefore, this is 6. I'm using a lot of math here that's just kind of intuitive. So this is not isosceles, it's equal angular, so it's equal lateral. All angles are the same, all sides are the same. This is half the side. And now I could use Pythagorean theorem. Remember when you set up your Pythagorean, A is a leg, B is a leg, C is a hypotenuse, has to be. So I go, I know A, so I'm just writing A squared plus B squared equals C squared. We want A is, oh, they just want to know what AD is? AD is 6. Well, I'll go ahead and prove it. I can't really prove it because I've already assumed that it's 6 right here. Sorry, the problem's over. I gave you too much information. So and this one's also 30 degrees because that gives you a 30, 60, 90 triangle. 30, 60, 90s are always in the ratio of 1 to 2 to root 2. Um, I'm sorry, 1 to root 3. Uh, and so these things, this side and this side, are a ratio of 2 to 1. So if this one's 12, this one's 6. So you're just done. But it's still a problem with all the math we've been doing. Like they would just throw that one in there. But oh well. Simplifying radicals. See, these aren't like radicals. Like radicals have to have exactly the same thing inside. They don't have to have the same thing on the outside. So these can be combined, saying I got 8 of these root A's. But if they don't have the same radical, like these don't, then you really can't add them. But you have to make that decision after you simplified them. So for example, the root 8 here, remember we've been talking about how you factor these things. Root 8 I'd write as 4 times 2. So this expression is the same thing. And then I can square root the 4. So it's 2 root 2 minus this root 2. I'm going to write it as 1 root 2 because that's what it means. So you can see this 2 minus 1 is the math you do. The root 2 you just carry along because it's like I'm counting the number of root 2's. 2 of them, take away 1 of them, I'm left with 1 of them. And that's this guy here. When written above that an irrational denominator, so we're rationalizing the denominator. This is like problem 1. I multiply by the conjugate. Remember, that's a 7 under there, Mr. Dog. So remember, when you multiply by the conjugate is same number or same sign on the rational part, opposite sign on the irrational, and do the same to the top. I always wrap these things in parentheses. So on top, the 8 gets taken times both those. 8 times 3, 8 times the root 7, we just write as 8 times the root 7. It's not only outside stuff gets multiplied by the 1 on the outside here. And then on the bottom, here we go. 3 times 3, 9. Now here comes the magical part. I'm going to kind of write these things off to the side. 3 times root 7. And then you're ready to start inside here and take this one times this, but that's a negative times a positive 3. So you get negative 3 next to the root 7. And these just 7, and those two just cancel out. So the last thing that gives me something that stays in the denominator over here is this negative root 7 times the positive root 7, which is a negative root 49, 7 times 7. But see, that's the perfect square that makes the radical disappear now. So we end up with just a 24 plus 8 root 7 on top. But on the bottom, we get a 9 minus square root of 49 is 7. So we end up with 24 plus 8 root 7 over 2, and both the 24 and the 8 can be divided by the 2, giving you that final answer. Ching. All right, in this equation, y equals x squared minus a. A is positive constant. So it's some number, 2, 3, 4, negative a half, 3/8, just some positive number. Well, I guess not negative 3/8, but some positive number. And the graph of the equation in the xy plane is a parabola. Okay, following is the equivalent form of this equation. Hmm, That's kind of interesting, but this one would work. I've never seen a question quite like that, but yeah. So we could treat this like a difference of squares. A squared minus b squared is a minus b. I'd square root this, that gives me the a. And a plus b. They just always come out like that. I square root both these things as long as they got this minus sign between them. Square root them both, it tells you what goes here and here. And so if I've got x squared minus a, I could do that same thing. I'd say square root this, well, that gives me x. Square root that gives me minus root a, because I can't really square root it. And then I get the x plus the root a as well. And this thing, if you wanted to, we could just multiply it together, and I could prove to you real quick that it does give you the original. So you can see that going on. It's plus x times x times root a looks like this, x times root a. But this now is negative times an x, so it's negative x root a. Those two cancel. And your last multiplication, the negative root a times root a is negative root a squared, but you can square root a squared, and that is x squared minus a. So that certainly, this product is equivalent to that right there. And number 9, x. All right, got ourselves a radical equation. We're going to get him by himself. Why isn't he by himself right now? He's got a 2 over here, and he's got this minus 8. Undo additions first. Leaving the radical here in red so we can see what we're getting alone. Still not alone. It's got a 2 in front of it, so I'll divide both sides by 2. Now the radical is alone on the right. And on the left, when I divide everybody by 2, I get that. Once the radical is alone, if you remember, we said square both sides. Right side cancels out the square root when I square it. Left side is that darn binomial we talked about. I use the definition of squaring and take it times itself. I'm going to cut to the chase here, though. This comes out to 9 squared plus 20, or 9x squared plus 24x plus 16. That's just doing all these multiplications. There's the right side. This equation is quadratic, so we got to get it equal to 0. So start on one side and get rid of everything. I generally, if my squared's on the left, and I move everything to the left. So on the right side, everything adds up to 0. On the left side, 9x squared. Ooh, these cancel out. 16 minus 17 minus 1. That's awesome. This relates so much to the one right above it. This has got two terms. It's got a minus sign. And so we said you can just square root this, square root that, and essentially then write it as 3x. Square root of 1 is 1 minus 1. And then you have to do 3x plus 1. That's how it factors. Set each factor equal to 0 and solve them. 3x equals add 1, divide by 3. Subtract 1, divide by 3. And you're done, except for it was a radical equation, so we got to check these darn answers. We have to check both 1/3 and negative 1/3. Okay, so I'm going to check the positive one first. Hey, 1/3 of 6 is 2. All right, does that equal 24 times the third plus 17? Let's see here. 2/3 of 24 is 8. 2, that's 8 plus 7. Oh, that's 2 times 5. That's 10. That 1/3 did not work. Let's try negative 1/3. See what that does for us. So I'll put negative 1/3 in there. That gives me 1/3 of 6 is still 2, but now it's a negative 2. And I'll check the right-hand side. 24 times negative 1/3 plus 17. So 1/3 of 24 is still 8, but now it's negative 8 plus 17 equals 2 times 9, which is 2 times 3, which is 6. But those don't match. This thing must have no solutions. But now I'm going to double check it. I'm going to pull out my Desmos and I'm going to graph. Oh, shoot. When I checked it, I goofed up my check. Look at my check. I forgot to put the -8 on my check. Oh, goodness. This one does work because this would be -8 minus 8. 6 minus 8 is -2. It does check. I wonder if I goofed up my positive one by not putting in the -8 at the end of this thing. I better check him again. Teach me to do math on a Saturday afternoon. Ah, all right. Let's see if I can clean this up. I'm sorry, Maddie. All right, now I'm gonna check the so the negative 1/3 worked. So we got to keep that guy. I got to check that positive 1/3 again. So 6 times positive 1/3 is 2. Check the other side. 24 times the positive 1/3 plus 17, and then this -8 that I forgot before. 3rd of 24 is still 8. 2 times the square root of 25, that's still 10. But 10 minus 8 is 2. They both work. And now I'm going to test it on my Desmos so I can show you how you could do it on that as well. So if you gave me this equation and I'm allowed to use Desmos, I would graph the left side. I'd go y equals 6x. There's all the answers that make the left side true. And then I'd graph the right side. Y equals square root. I got to get a 2 in front of it. Square root of 24x plus 17 minus 8. There we go. And I'd zoom into that thing and I'd ask my calculator, man, these things are hard to tell. If I can see the red one hits that blue one, if I can separate it just enough, maybe you could see the red one coming through and the blue one crossing it twice. Great thing about Desmos is you can tap it where you think they are, and it will tell you the X values where they cross and the Y values. So when they cross at the top one, 0.1 or 0.3333 comma 2, and they also cross at the bottom negative 0.333. And that those 0.333s, if you aren't aware of that, those are repeating threes, and repeating threes are 1/3. So there's the 1/3, and this one's the negative 1/3. And they both work. All right. Last page, or was that all? 1, 2, 3. I think we're done. Alrighty, hope that helps and wasn't too messy. Good luck and let me know if you got questions.